Greetings to all my tech heads out there in the KevTechify Nation, and if you're new here, welcome. In this episode, we're going to be looking at the IPv6 packet. We'll be discussing the limitations of IPv4. Then we're going to look at the IPv6 overview. Then we're going to take a look at the IPv4 packet header inside of those IPv6 packet header. And then finally, we will examine the IPv6 packet header. This episode is part of my series on Introduction to Networks for the Cisco Certified Networking Associate, also known as the CCNA. I'm Kevin here at KevTechify. Let's get this adventure started. There are some limitations with IPv4. There are three major limitations here. One is the IPv4 address depletion. We ran out of addresses a long time ago. There are no more addresses available for people to go get them from the respective organizations and set their devices up. There just are no more addresses right there. To make IPv4 last as long as we've had private addressing and we've done network address translation, NAT, and that has ended the idea of end-to-end connectivity. Because we're doing this NAT, because we have this private addressing, end-to-end devices no longer communicate with each other. And because of this NAT we're running on the network, it was supposed to be a temporary solution, but it's turned into a long-term solution. And there are side effects, and they're causing issues on our network. So NAT has added this complexity to our networks that was never supposed to be there. IPv6 was developed by the Internet Engineering Task Force. They came up with this solution. IPv6 overcomes a lot of the limitations that IPv4 is now presenting to us. Some of the improvements IPv6 provides us is it has an increased address space. If we look here, IPv4 gave us 4 billion addresses. That's 10 to the 9th power. That's a 1 followed with 9 zeros. IPv6 gives us 340 unidecillion addresses. That's 10 to the 36th, or a 1 followed by 36 zeros. That's how many IPv6 addresses there are. IPv6 also gives us improved packet handling. It's a simplified header with fewer fields in it, which makes it easier to process. It eliminates the need for NAT. IPv4, we have to use NAT to get all the devices we want on the network. IPv6, we don't have to use NAT, so we eliminate that layer of complexity. When we look at the IPv6 packet header, we look at it, it is just as long as the IPv4 header, but we've removed several fields to simplify it. The header is fixed. It's 40 bytes long, just like the IPv4 was. There's several fields that have been removed to improve this performance. Some of the fields that were removed from IPv4 include a flag, a fragment offset, and that header checksum. We've removed these headers. Now, it's the same length because the addresses are so much longer that it takes up that space, but there's less fields to process. As we look at these fields, we have the version. That is the same thing from there. Version 4, version 6. Traffic class here, once again, has to do with quality of service, wanting to make sure your real-time traffic gets through your system. So voice over IP phone calls, video conferencing, that gets priority over web page browsing on your network. We have a flow label here. That's this next one. It informs the device to handle identical flow labels the same way. Then we have the payload length. Right there indicates the length of the data portion. So what follows the header? How long is it? That's what we're looking at. The next header here identifies the protocols that are used in the layer 4 and above. So is this ICMP, TCP, UDP, and then the hop limit. This replaces the time to live in the IPv4. It can only go through so many hops. It can go only through so many routers before that packet, if it hasn't reached its destination, is deleted. And then we have, of course, our source address and our destination IP address. I hope you are liking this episode on IPv6 Packet. If you have the time, please leave a comment and let me know what you think about the IPv6 Packet. You can also visit my website at KevTechify.com for all of my details and how to get these episodes in video and podcast form. The next 3 slides are going to have some screenshots of Wireshark. That's a tool that allows us to actually look at the traffic going across our media. And we're going to look at IPv6 headers to examine them and see what's happening. Here in our first screenshot, we can look. The highlighted packet here is 46. We can see that that's highlighted there. And then the source IP address here, listed right here, continues on a little bit. It's 2001:6F8. And we can see that that's the starting there of our source address. And we can see by looking at this that it is a global unicast IPv6 address by the 2001:6F8. You can see that's a global unicast IPv6 address. Now you can see the destination address. That starts with 2001:6F8 also. That is also another global unicast address. Then if we look over here in the protocol field, we can see that it's a TCP protocol we're doing. And if we slide a little bit more over to the info line, we can see that it is trying to establish a connection. And if we look a little bit further over here, we can see that it's trying to establish a connection to make an HTTP request. So we're trying to contact a web server. Now, when we come down here, we can look and see that we've expanded out the IPv6 protocol. Once again, here's our source address. Our destination is off the screen. We've said that our version here is IPv6. When we look at this, if you translate this binary here into decimal, it comes out as a 2 and a 4. You add that together, that gives us our version 6. Well, that's kind of interesting. The next field is our traffic class field. Here, the same function as the differentiated service fields in IPv4. This gives us our quality of service. Basically, it's a web request, so there's no special priority on it. Next section, you can see here, this is the flow label. The purpose here is to maintain the same packet flow through routers and switches to help real-time applications that need packets to arrive in the same order. The next field here is the payload length. So it's 40 bytes long. The next header field right here is the same thing as IPv4. It identifies what traffic for layer 4 we're having. So this is a TCP traffic. Top limit is 64, so it can go through a maximum of 64 devices before this packet is deleted. Once it gets down to, every time it goes through a router, it's subtracted 1. So first time it goes through a router, it'll go down to 63. Next time, 62. Once it's decremented all the way down to 0, we will delete that packet from there, because we're assuming that that destination is not reachable in 64 hops. Then we have the source and destination IP addresses, and that, looking here, that's what we have for our data. Let's take a look at the next screenshot. Here we have packet 49 highlighted. That's the gray line through there. And as you can see, we have now made a connection to the web server, and we've actually put in a GET request to it. Look down, we've expanded out our IPv6 protocol. Once again, we have our source and our destination IP addresses here listed out. The information looks pretty much the same. We have the same version number, we have the same traffic class, same flow. As we look through here, getting down to the bottom here, we now can see that we have transmission control protocol parts in here. We have our source port, our destination port, where we're headed to port 80 there, and that we are using hypertext transfer protocol right there on the bottom. Here's the third Wireshark shot we're going to look at for IP version 6. As we're looking here, frame 1 is highlighted here. You can see that we are doing an ICMP version 6 neighbor solicitation. So we're trying to find out who our neighbors are at this point in time. We'll see the source address here is not a global unicast address. This address right here is not a global unicast address, but it's a link local address, meaning it's on your network. We can tell that from the FE80 here. The FE80 says that it's a local link address. The local link address also is using EIU64 to resolve the interface identification portion of the address. We can tell that right here by these values here, the FF:FE. That identifies what we're trying to resolve, that interface identification portion. The destination address is an FF02. So right here's our destination IP version 6 address. It is an FF02. Once again, this is saying that this is a multicast packet. We're sending this to a bunch of devices on our network. Not everybody, it's not a broadcast, but a select group of devices will get this. If we look over here at the protocol, we can see that it's ICMP version 6. And once again, it is a neighbor solicitation packet. What this is here basically is the ARP request. The ARP from IP version 4. This is IP version 6 version of that. The network solicitation. If we look down to the expanded details down in this area, we can see the version, the traffic class, the flow label. We can see all that information, all the same from before. The next header field here, once again, we are identifying it as ICMP version 6. That is identified by the value in this field is actually a 58. That 58 then corresponds to ICMP version 6. We have a 255 hop limit there, meaning we can go through 255 devices. That if we reach our 255 hops, once again, every time it goes through a router, it subtracts 1 from that number. If we get down to 0, then we're going to assume we can't reach our destination. We're just going to delete this packet. Sort of like the time to live from IP version 4. Then we have our source and destination addresses. Once again, this is a link local address for our source. Our destination here, we have this as a multicast address. At the bottom, we can see that there's an expandable field here for ICMP version 6. So if we wanted to get more information about what is happening, we could expand that and go ahead and look into that. It was my pleasure to provide you with this wonderful episode on the IPv6 packet. If you like this episode and you got value out of it, and of course, depending upon what platform you're using, please click that like button, leave a 5-star rating, give me a comment. This all helps me bring you more great content. Please take a minute to subscribe to my channel. All of my socials and contact information are on my website, KevTechify.com. There you can find out how to get all these episodes in video and podcast form. In the upper right is my playlist for my series on Introduction to Networks for the CCNA. In the bottom right is one of my favorite videos that I picked just for you. Thank you so much for watching this episode of my series on Introduction to Networks for the CCNA. Once again, I'm Kevin. This is KevTechify. I'll see you next time for another great adventure.